wanted to walk you through a few more examples of expected value. But first, I wanted to talk a little bit more about what expected value means and how it could be valuable to you. We'll sometimes hear expected value described as expectation. So instead of saying expected value, you could say find the expectation. And when you hear find or evaluate or calculate expectation or expected value, what that's asking us to do is to determine what the expected results would be over the long term. So if you were talking about a game of chance, how much would you expect to win or lose over a long term, over playing the game many, many times? At the end of the day, how much did you win or lose? The key there is that it's over the long haul, over the long time, after you've played many times. And we could relate this back to section 11.1 and comparing that to the law of large numbers. Now, the law of large numbers had to do with probability, not exactly expected value, but expected value is looking at over many cases, what would we expect to gain or lose? So the reason that some people will still play a game of chance, even though the expectation is maybe that you would lose over the long haul, will sometimes choose to play a game of chance because winning that lottery ticket, just that one lottery ticket where you could win $30 million might be worth the risk, where you know, well, my chances are really small, but I'm going to do it anyways because that payoff is so good. But let's look at some examples. Here's the first example. Zelda is opening up a business and she's coming up with her business plan, and someone at the bank or somewhere has helped Zelda determine whether this is going to be a profitable business or not. So Zelda's opening an antique shop. In the first year, she estimates that there's a 25% chance that she'll make $20,000. And there's a 40% chance that she'll break even, 35% chance that she'll lose $30,000. Determine her expected value for the first year in business. I'm going to use this chart for each of these expected value problems, and you might or might not find this chart to be helpful, but if you struggle at all with these problems, I do want to encourage you to make a chart like this each time you're trying to calculate the expected value. So we've got 3 different outcomes are possible. Zelda could make $20,000, break even, or lose $30,000. So the gain or loss is written as either a positive or negative, or in the break-even point, it's a 0. And then I have the probabilities written in. So the first step to using this chart is simply filling in the information from the problem into the chart. Now all I have to do is apply this information to the formula. Expected value of X is the probability of the first outcome times the gain or loss of the first outcome. So we're going to call making $20,000 the first outcome. And so we have the probability of making $20,000 is 0.25. And if she does do that, the gain is $20,000. Plus 40% chance of earning or losing 0, plus 35% chance of losing $30,000. When I multiply these out, I get 5,000 plus 0 minus 10,500, or an expected value of negative $5,500. So what does that mean? It means Zelda can expect not to make, but to lose $5,500 in the first year. Now, why might she still choose to go forward with this business? Well, maybe she knows that that first year she'll be at a loss, but has anticipated that the years following will all be gains. Or there could be any number of reasons why you might still choose, even though the expected value is a loss, you might still choose to move forward with a decision. But at least you have it understood exactly what the outcome could be expected. Let's look at this next problem. It's a rolling a die game. Alyssa and Gabriel are playing this game. Alyssa rolls a die, and if she rolls 1, 2, or 3, that's our first outcome. Gabriel gives Alyssa $3. So if I'm doing Alyssa's expectation, which is the part A of this question, I'm going to look at it from her perspective, and Alyssa's perspective is that she gains $3. Rolling a 4 or a 5, Gabriel gives Alyssa $2, so that's for Alyssa, it's a gain of $2. And then if she rolls a 6, then Alyssa's gain is a loss of 14. So this part A is looking at everything in perspective of Alyssa's point of view. She could gain $3, gain $2, or lose $14. And we're trying to determine, she played this game again and again with Gabriel, what could she expect to win or lose on average for each game. So I've calculated the probability 3 out of 6, 2 out of 6, and 1 out of 6. And although we usually would want to reduce fractions, I wanted to show you that leaving these fractions in their unreduced form is actually going to be beneficial in getting the final calculation because it will give us a common denominator. So I'm going to multiply the probability of 3 out of 6 times the gain of $3 to get 9/6. The probability of 2 6 times the gain of 2. So that 2 6 times 2 would multiply out to 4 6. 2 times 2 is 4, 6 times 1 is 6. 1/6 of negative $14, or 1/6 times negative $14, would give us negative 14 over 6. And now to add these, I'm going to add 9 plus 4 plus negative 14, gives us a negative 1 over this common denominator of 6. So negative 1/6. When I put that into a calculator, 1 divided by 6, I get negative 0.16 repeating. If I were to round that to the nearest cent, we could say that therefore Alyssa can expect to lose 17 cents per game over the long haul, or over the course of playing again and again. Let's look at one more example, and we'll, I'm sorry, let's first look at Gabriel's expectation. We'll do the same thing and see that, of course, if Alyssa is losing 17 cents, Gabriel will win 17 cents per game over the long haul if they played again and again. Let's look at another problem. This is a good problem. Let me go to a clean page here where we can just look at the problem. Here's the setup. We're going to look at this case right here. Here's the setup. You pay $15 to play this fun game, the envelope game. It's a game of chance. So you pay 15, and you get to keep whatever check is in that envelope. And for this case, this third case, we're going to say that the first envelope has nothing in it. That's empty. The second envelope has $2, $5, and $20 in each envelope. So let's look at some different things that the person who's trying to talk you into playing this game might say. First of all, we'd notice that 1, 2, 3 of the envelopes are winners, right? You win 3 out of 4 times, or 75% of the players are winners. But what you have to always take into consideration, of course, is what did you have to pay? So did you really win? Did you really come out ahead? Because that blue envelope, you've paid 15 and gotten nothing. The green envelope, you paid 15 and get 2 back, so you've still lost $13. The red envelope, although you get a $5 bill or a check for $5, you've paid 15, so you've still lost $10. The only envelope where you come out ahead is that yellow envelope where you come out a whopping $5 ahead. So I can tell up front by thinking through this problem that it's not going to be a very profitable game to play. But let's work out the expectation and look at it piece by piece. We've got the blue, green, red, and yellow envelope. Gain of, or actually a loss of $15, a loss of 13, a loss of 10, and a gain of 5. And that comes from having 0 in the envelope and paying 15, 2 in the envelope and paying 15, 5 in the envelope and we paid 15, $20 in the envelope and we paid 15. And all 4 envelopes are equally likely to happen. We've got 1/4, 1/4, 1/4, and 1/4. So if I worked out this expectation, I had to do 1/4 times negative 15, plus 1/4 times negative 13, plus 1/4 times negative 10, plus 1/4 times 5. I do want to note that since all 4 outcomes are equally likely, there is another way to see this calculation, is I could factor out that 1/4 and add the negative 15, negative 13, negative 10, and positive 5 and come out with the same outcome. I'm going to get negative 33 times 1/4, and that's going to give me the same outcome. So notice that since they're all equally likely, that would work, but just doing the expectation, and I'm going to keep the denominator, even if these simplified, I'm going to keep them with that common denominator so that when I go to add them, I'm just doing the 1 times the negative 15 plus 1 times the negative 13 plus 1 times negative 10 plus 1 times 5 is the numerator all over 4. When I do that calculation, I get negative 33 over 4, and I could divide that out to get negative 8.25. Therefore, what I could say for this question is that therefore you could expect to lose $8.25 each time you play. Now, let me be clear about that, because there's not any single one round of this game where someone loses $8.25. But what we could say is that on average, after you've played many times, on average, the average loss is $8.25. Well, I hope that this set of examples helps you a little bit more in seeing the approach written out with that chart. If you do have questions, I hope that you'll let me know. I'm happy to work out additional examples. I'm also happy to meet with you in the virtual office. If the hours that I'm available online don't fit your schedule, let me know. We might be able to work out an appointment time also. But thank you so much for the work you're doing to be successful in this course, and let me know what I can do to help you.